we'll finish the mapping today here. So I did a quick review on second order system in the previous lecture. Basically, second order system is a very representative type of system when you design for control system. Many high order systems can be reduced to second order. Given a typical second order system, its poles are listed over here. So there's a real part, there's a imaginary part set here. So when we do mapping, our essential formula is this, basically z equal to e to the power st. So any poles in the s domain will be mapped through this equation into the z domain, right? And that's the result of impulse sampling, basically. In the second order system, and I also showed you basically a number of specifications that we can make use of for control design: sampling time, percentage overshoot, and the peak time, time constant, bandwidth, or rise time. So those are the formulas that we can just ready to use for design of a control system, right? Yeah. So and I have given you a simple example. Basically, if you have a certain specification like this, and what does that mean, right? In terms of the region in the S-plane that covers the criteria for the specification. So this is in terms of settling time. Okay, settling time. Now, specifically, another example I wanted to go over before we look at the mapping is, let's look at an example here.
Dr. Chad,
yeah.
I just have a question from those formulas you had.
Yeah, which one?
Either the time constant or the zeta. I forget which one it was.
Okay.
There was a ln squared MP.
Here, yeah.
So is that just ln MP squared? So 2 ln MP in the denominator?
Oh no, this is a pi squared ln NP bracket squared.
Okay. Okay.
Right.
Oh
yeah.
Yeah. Okay. That makes sense.
Yeah. Cool. Yeah, this is a good formula. So to back calculate damping ratio given a specification on the percentage overshoot, right? Yeah. Okay. Now, because we're talking about digital system design, so when you design a digital system and you design basically for the mapping, inevitably you have a sampling. So now the problem here is when you have a sampling, right? The choice of the sampling frequency or the sampling time will actually change significantly sometimes, okay, in terms of the system response. So let me give you an example right here, okay? So let's say here is a continuous system. Very simple system. As a matter of fact, maybe there's even no control here. You just close a loop, okay? So you have a plan and then you close a loop. And if you derive the closed loop transfer function for this one here, and you'll get this is basically 1 over s squared plus s plus 1. That's the closed loop Laplace transformation, okay, for the system. So this is exactly in the format of the second order system here, right? Yeah. So if I do a little comparison with the format of second order system, so basically you see the 1 here is omega n squared, right? So that basically means the omega n equal to 1 for this system, and then 2 zeta omega n equal to 1. So you can derive the zeta value, which is 0.5. So that's the closed loop system for this one, which you should expect natural frequency is 1 and damping ratio of 0.5. Okay, yeah. And if you plot this out, okay, because zeta equal to 0.5, as we in the previous lecture I mentioned this one here. When your zeta is 0.5, it's approximately about 16% of overshoot at here, right? So if this is a steady state, then okay, that's what probably will look like, okay, given the step input to the system, okay, and then you get this one here, okay, yeah. Now, if we're gonna basically discretize the system, right, and we can take a look at simple case study here. So let's see, I'm gonna put a zero order hold at here, and then same plant at here. Okay. And then close the loop. Okay. So that's simple, basically, this digital system now. Okay. So, as a matter of fact, this is very much similar to one of the midterm questions, right? So, giving this, and then you're asked to derive the closed loop pulse trans function, isn't it, right? Yeah. So, let's say we take a sampling time equal to 1. Okay, take sampling time equal to 1, and then you can derive the pulse transfer function for the closed loop. Okay, and then the results of this derivation will be this. Okay, so that will be the results of the pulse transfer function by introducing a sampler and a zero order hold into the system. Okay, then from here, this is based on the sampling time t equal to 1 at here. Okay, from here you can derive the pulse of this digital system. So basically set the denominator to be 0 and solve for the z. We'll get 0.5 plus minus j 0.618 is the pulse of this system here. Okay. And then for this particular pulse here, you can write it in terms of the magnitude and angle. Okay. So that basically gives you an R value and a theta value at here for the pulse in the digital domain at here. Okay. All right. So now, what I wanted to do at here is to look at what does this t equal to 1 do to us in terms of the system response. Okay, what will be the difference basically comparing if I compare the response of the digital system with the response of this continuous system here. Okay, so how do I compare is basically, so here is your pulse of the digital system here, right? Here's R and theta corresponding to the pulse. Now in the previous lecture, and I did derive a simple formula here. Basically, it's this formula at here, right? If you have R and theta in the discrete system, and that will be the corresponding zeta omega n can be found through this formula at here, right? Yeah. So if this is my R and theta here, then I can calculate the zeta, okay, according to that formula. So negative ln n over ln n squared plus theta squared. Okay. So if I do this calculation, I will get 0.25. Okay. And I can calculate omega n similarly, which is 9.91 if I do that calculation. Okay. So now you can immediately see originally what's my damping ratio, 0.5 and 1, right? And with a t equal to 1 sampling, the digital system will end up with a new pulse, right? I mean, this pulse is not the same as the continuous system, of course, and that pulse corresponds to a damping ratio 0.25, and omega n is this. So both of them are actually smaller now, right, than the original values. But then what does that mean? Basically, if you look at this damping ratio 0.25, and if I'm going to use MATLAB to sketch or to simulate the system with the step input at here. So basically, if I'm going to plot this MATLAB here, and then you probably will imagine. So essentially, anyway, right? See what I'm saying, right? So that's basically will be the response, the discrete response unit step input for this particular system. Now, if you look at we are purposely draw the red one, the discrete one here, which will have higher overshoot now. Because why? The zeta here is 0.25 now, right? Which is 0.5 in the continuous system. Okay, yeah. So that basically what you need to bear in mind is your choice of sampling time, okay, will basically once you discretize your continuous system, it will always to a certain extent modify the behavior of your original continuous system, basically. Okay, yeah. And you can, of course, you can try t equal to 0.1, then you would expect this probably would be getting closer to 0.5. Okay, yeah. Okay, so just that's something just to bear in mind here.
Can you do better than the continuous, or will always be off?
It will always be off. Yeah. So that's unfortunate. Yeah. Yeah. So digital is always just approximation of the continuous system, right? Yeah. Okay, but digital sometimes do actually outperform continuous system though. Well, I should be careful about that, but yeah, because so far, many technologies, right, essentially is all using the digital signal to approximate the actual world. So, okay, so now let's dive into the some of the specific mapping at here. So I'm going to look at the different cases. Okay, so let's look at the type number 1. I'll call it mapping. Okay, mapping of the constant attenuation lossy. Okay, so mapping of the constant attenuation lossy here. So what does the attenuation mean? So for example, right, let's say given continuous system pole at here, so sigma plus j omega. Okay. So if it's a second order system, right? For example, if a second order system, your sigma is that negative zeta omega n, right? Yeah. Okay. So attenuation, basically, if you look at the mapping, this gives you this mapping at here. So this e to the power of sigma t, so this term at here, right? This term at here basically is the term constrains how fast it will attenuate, right? Yeah. So if this is a negative number, it will attenuate. It's a negative number because we always choose looking at the left side of the S-plane. If it is a very big negative number, then it'll decrease faster. Okay. So this constant attenuation basically means when sigma here, right, is constant. Let's write it down here. So if sigma is constant, then what happens? So if sigma is constant, then in the S-plane, okay, in the S-plane at here, okay, so let's look at the cases of sigma is constant. So the imaginary axis basically is a special one, the sigma equal to 0, right? And then if you go over here, so it could be constant sigma 1 here, it could be constant sigma 2 at here. But basically, you can always draw a line, vertical line at here. You can always draw a vertical line. So any point along that vertical line will have a constant sigma value, right? Yeah. So that's this green one here, including the imaginary axis. This is what we call constant attenuation loci, right? So this is one locus, right? So any one of the vertical ones a constant attenuation. And how is that going to map to the z-plane then, right? So in the z-plane, if you look at the way he it maps, it's basically, this is how it maps. Z equal to e to the power of st, this is how it maps. If sigma is constant, then that means the e to the power sigma t is constant. Okay, so this is r, right? This is your r here. Okay, this is your R here. Okay. So now let's take a look at the example, the 3 green lines that are here. Let's consider e to the sigma equal to 0 first. So if sigma equal to 0, then the R equal to e to the power 0, which is 1, right? So basically means for any one of the points along the imaginary axis, it will be mapped to where? To the unit circle, to the boundaries of the unit circle here, right? So that will map to here, okay? Yeah. And this unit circle has a magnitude, a radius of 1. And this is in Z plane. Okay? And now you look at sigma 1 and sigma 2 now. Okay? So sigma 1 is a constant. If sigma 1 is constant, then you have a e to the power sigma 1 t, right? And this is e to the power sigma 2t. Okay? So apparently, this is another r here, this is another r at here. Okay? So sigma 1 is less than 0, then this r value will be a value inside or outside this circle for this one here. Inside. So you would have a circle inside here, and that radius, right? The radius at here is e to the power sigma 1t, right? And then sigma 2, and this is on the right side of the plane, so you can imagine it's going to be basically outside this unit circle here, right? So that's mapped to here, and this one has radius e to the power sigma 2t. Okay. So that's how a constant attenuation loci being mapped to the Z plane. They're all going to be mapped to a circle, right? It just depends on where the constant loci is, and that radius of circle will vary accordingly. Okay. That's the first type, okay? The simple type here. Let's take a look at the second type. Let's look at the mapping of the region, okay, of minimum settling time, TS. Okay. So here the criteria is slightly different. So basically, if you have a minimum settling time given, right, or the region of the minimum settling time, how is that region being mapped to the Z plane? Okay. Settling time, as you recall, we actually did that in the previous lecture here. Basically, there are 2 different types of settling time, right? So there's 1% of settling time, there's a 2% of settling time formula. Either one of them has a constant in the numerator, and the denominator has a zeta omega n over here. Okay, yeah. So let's use maybe 1% to illustrate this here. Okay, yeah. So first of all, where is the region of this minimum settling time? Okay, so this is S plane, right? So settling time, we're talking about 4.6 over omega n at here. Okay. So minimum settling time basically means you need to satisfy certain constant value that is less than that. So let's say 0.5 settling time or 0.2, so less than that value, right? That's called the minimum settling time here. So basically, if you look at this relationship here, the bottom here is a zeta omega n, right? You could basically, if a second order system, that's basically what sigma is over there, right? Yeah. So all you need to do is, let's say here is the vertical line at here, so representing certain sigma value, which is 4.6 over TS, okay, 4.6. So there's negative here because sigma equal to negative zeta omega n. Okay, And minimum settling time region basically refer to the region on the left side of this vertical line, right? Left side vertical line. So this is actually quite similar to type 1, isn't it, right? So type 1 deals with only this one vertical line, okay? So one vertical line is the constant attenuation low C. But now you're dealing with, it's a region which is on the left side of the vertical line, okay? So the idea is plus the vertical line plus this whole region on the left of that, and where would that be mapped to in the Z plane? And this vertical line will be mapped to a circle, okay, with a radius of e to the power sigma 1t, and you can imagine then everything on the left side of the vertical line will be mapped to the inside of this circle here, right? Inside circle. So in other words, okay, if you're going to design, let's say, in the digital domain for a certain minimum settling time, then your choice of the pose in the Z plane will be anywhere within this circle at here. Okay, so if you pick a circle within this not a unit circle necessary, within this circle, then you can guarantee that region of the minimum settling time. Okay, that's type number 2. So type number 3. Okay, let's look at the mapping of constant frequency low C. Okay, constant frequency low C. Constant frequency. Let's still start with this sigma plus minus j omega, and this is your pose, okay, in the S plane. Okay, and with the mapping Z equal to e to the power st, give us e to the power sigma t, and then angle omega t, right? Just one more step right here, you see, which is e to the power sigma t angle omega t. Okay. So bear this in mind here now, and then let's take a look at the constant frequency here. Okay. Constant frequency basically means, if you look at this pole at here, this is the pole, real part, imaginary part. Okay. Imaginary part is the omega, it's the frequency. So if omega is constant, so it basically means what? You would draw a whole bunch of horizontal lines at here, right? Whole bunch of horizontal lines. Each one of the horizontal lines are representing one frequency. So let's say this is j omega 1, okay, and this is j omega 2, okay. So I should write this is omega 2 at here, and this is omega 1 at here. Okay, yeah. Each one of the line corresponding to a natural, not a natural frequency yet, corresponding to a frequency omega, right? Frequency omega. Okay, and let's say this is omega 3, right? This is omega 3, for example. But there's another thing that you have to bear in mind. Okay, in previous lecture, we noticed, basically for a discrete system, the frequency basically always change from negative pi to pi. That's your maximum frequency, right? You cannot be any faster than positive and negative, positive and negative. Okay, so then what we have in the previous lecture is we have the so-called what? A primary region. So the primary region goes from negative j omega s over 2 to positive j omega s over 2, right? That's a primary region. And you could go beyond that primary region, but then it's basically kind of repeating itself, right, in the Z plane. Okay? Yeah. So I'll purposely at here just restrict those omega 1s, omega 2, omega 3s within the primary region, and then we'll look at the mapping at here. Okay? Yeah. So let's see. Let's look at how is this horizontal line, right, at omega 1 at here being mapped to the Z plane, okay, to the Z plane here. Okay. So if you pick up any point along this horizontal line at here, and then plug it into this mapping equation. Okay, mapping equation here. So for example, I get e to the, so because each one of the points have a different sigma, right? But the same what? Omega, right? The same omega. So it's sigma t and then ej omega 1 t, right? So this is for the omega 1 here, okay? And that basically is angle omega 1 t, okay? Angle omega 1 t. Okay. So if you look at this one here, then how does this one, omega 1 is constant, how does this look like in the z plane? Here's your r, here's your theta, right? So you have a basically asking you to draw a vector, right? The vector has a time changing quantity magnitude, but the vector pointing to the same direction, right? Exactly. So you would draw this from here. So this is how much angle? Omega 1 t, right? Omega 1 t. So that line over here, right, will be mapped to this reading lines over here, okay? Reading lines over here. Yeah. Now, if you go a little bit deeper here, let's say I start the point over here and then moving all the way to the right, right? Yeah. And you can literally say, as it's at infinite left, where it is, it's here, right? It's here. Okay. If this is A here, this is A. Okay. And then as it goes to the imaginary axis, so it'll be somewhere here, right? And that particular point, what's so special about it? Exactly, right? It's at a 1. So that basically this is the point crossing the unit circle, okay? Crossing the unit circle. And then if it keeps going on this side here, then you basically, this is a B over here, okay? Yeah. Okay, so now take a look at comparison now, right? Let's take a look at omega 2. Okay, omega 2 here. Okay, omega 2 is a bigger value than omega 1, so really depends on the actual value. Then omega 2 probably will be reading lines over here, and that angle, okay, this angle here is omega 2t, right? It's omega 2t. Good. So what about omega 3? Omega 3 is below the real axis. So it's a negative number, right? It's a negative number. And then it really depends on where omega 3 is. Let's say over here. Then it's from here to here. That's omega 3t, which is a negative angle at here. Okay. Yeah. Good. Yeah. Okay. So these 3 types. Okay. We have 2 more types today here. Okay. But let's take a look at the example first. Okay. I'll give you a region in the S-plane. So here's an S-plane. Here is a rectangular region in the S-plane. Okay. So you can extend all the boundaries out. Okay. So this is A. Let's see. This is C. This is B, D, E, F. Let's say G, H. So this region is essentially intersection of 4 straight lines here. Okay, 4 straight lines. So let's say suppose that this value, horizontal value, this is G omega 1, Okay, and this is H at here. This is J omega 2. So I'll use negative to represent the actual negative here. So this is negative. J omega 1, negative J omega 2, and the region is within the primary strip here. Okay, so this region is within the primary strip. So that's the two horizontal one. The whole two horizontal corresponding frequency omega 1 and the frequency omega 2. And the vertical one in here, okay, the vertical one in here, let's say it corresponds to here corresponding sigma 1. Let's say they call it negative sigma 1 because actual negative value, and negative sigma 2. Okay. So that's the two vertical line value over there. It's a rectangle, okay, so basically perpendicular on both ends, on the four corners there. Okay, so I want you to think about it. How is this region going to be mapped to the Z plane? Okay? And what does it look like after the mapping? So make use of the basically what we just learned, the three types, right? How does it look like after the mapping? So if you look at this one here, first one, basically the two horizontal ones are which type? This type 3, right? The constant frequency low C. And the vertical lines here are basically either type 1 or type 2, doesn't matter, because it's essentially a constant attenuation, right? Or a certain region of a minimum settling time. Okay? Yeah. So let's take a look at the actual mapping at it here, right? Take a look at the actual mapping. First of all, you can draw unit circles. Okay, you can draw the unit circles just for the reference. So let's see. I draw the unit circle over here. All right. So now I'll use the knowledge we learned for the two vertical lines here. Okay, the two vertical lines. They will always be mapped to two circles, right? So because the two vertical lines are on the left side, so the two circles will all be within this unit circle. And this negative sigma 1 is a bigger value, right? And then this negative sigma 2. Okay? And basically, negative sigma for the circle corresponding to the CD line here. Okay, the circle corresponding to CD. Probably you can draw something that is a little closer to the unit circle. Right, so this is C. This one here is a CD here, right? It's a CD. Okay. And what's the radius of this circle? The radius circle is what? E to the power of negative sigma 1t, right? Yeah. And then the AB line here is another circle, but this circle is on the more to the left, so it should be within this CD circle. So this circle right here is that AB line, and the R is right negative sigma 2t. Okay. Okay, so if I give you a condition, rather than the condition, if just a condition A, B, C, D, if we stop here, then what will be the region for the region between A, B, C, D in the Z plane? It will be where? It will be the region between these two circles here, right? Okay, yeah. And now let's look at the EF and the GH here. So EF is on the top of there, so it's a J omega 1. You know, it didn't give you the actual omega 1 value here, but let's just say omega 1, right, is an angle corresponding to this much at here. Okay, so that basically, let's say this is your omega 1 here, so omega 1t. So this is where that EF line being mapped to. And GH is bottom here, so GH, let's say I draw it over here, so that's your GH here, so this is your omega 2t, okay, omega 2t. And this is the GH line here. Okay, so you have 4 basically boundaries, 1, 2, 3, 4 in the Z plane. Okay. Now, the last step to sketch the region. So this is the region in the S plane. Then in the Z plane, where am I looking at? The region. So it's basically the intersection, right? They're overlapping here. So you're looking at what? Okay, so this portion right here. Okay, so this portion. Does that make sense? Yeah. In other words, the design in the time domain, okay, any post location in here, if you design the digital domain, then you need to pick a pole somewhere within this region in here. Okay? So then you'll set it, you have the same basically requirements in terms of the system performance. Now before we move on, this is actually will come back to us too. Now let's take a look at the relationship here, right? So if you look at the relationship here, this AB is perpendicular to what? To the EF. And AB is also perpendicular to GH, right? And that is the geometric relationship in S-plane. Okay, so in S-plane, you have 2 trajectory perpendicular to each other. Okay. Now after the mapping, where is AB? AB is which one? Is this? Which one? AB is vertical. AB is this circle here, right? It's this circle. Where is the EF? EF is this one, and GH is this one here, right? And what is the geometric relationship between this circle and the EF, the reading lines here? Geometric relationship. They are what? So when you have a circle and the reading lines perpendicular, right? Still perpendicular. Because basically if you draw tangent lines here, and that's perpendicular. So essentially what we call is that line is normal to the curve, right? Or that vector is normal to the curve, you know, whatever you want to say, right? Yeah. This is a very important actually property. Basically what we're dealing with here, okay, is called complex analysis. In mathematics, there's another branch called complex analysis, which purely deal with complex numbers. Okay, in the complex analysis, you have a complex calculus there. So over here, there's a property is called conformal mapping. Okay, conformal mapping. So what this basically means is, when you map from one plane, right, which this is basically S plane here, to another plane, with both a complex plane, right? Yeah. The geometric relationship will be retained exactly the same. That's called conformal mapping. So the 2 trajectories perpendicular here will maintain the perpendicular property after the new mapping here. Okay. Yeah. We actually will see this property shortly for the other 2 types. Okay. Yeah. Okay, so let's take a look at type number 4. Okay. So this one here is called mapping of constant damping ratio. Okay, so mapping of constant damping ratio low C. Let's first understand what does constant damping ratio low C means. Okay, this is in terms of the S-plane, right? So let's take a look at, let's draw S-plane in here. Okay, so this is S-plane. Okay. Now I'm going to go back to my second order system in here. Okay, second order system. So in the second order system here, you have two poles. Okay. And this is the two poles for that standard second order system in terms of damping ratio and the natural frequency, right? And it's basically real part plus imaginary part, and the imaginary part is called the damped natural frequency. Okay. Now, if I'm going to plot the poles in the S-plane at here, basically here is your real part, and then let's say this is your omega d, this is your imaginary part, right? This is your imaginary part, and that's the pole location. Okay, this is the pole location here. And then I'll construct a line, okay, in the S-plane, okay, passing through this reading lines passing through the current pole location, okay, the current pole locations over here. So if you do this, and we can construct angle theta over here, okay. Now once you have the angle here now, and I want you to calculate what is sine theta. Okay, what's the sine theta here? That's very easy, right? Sine theta equal to what? Equal to this side divided by the length of the hypotenuse, right? Yeah. And this side is how much value? Let's just consider the actual magnitude. That will be zeta omega n, right? Okay. And what is the length of the hypotenuse? The length of the hypotenuse basically is what? It's the sigma square plus this omega d square, isn't it, right? Okay. So the real part squared plus the imaginary part squared, and then square root. Where's the imaginary part? It's this one here. So now if you square this, and then plus the square of this, hello, what's gonna happen? Because there's both a zeta square omega n square, zeta square omega n square, right? Yeah. And then the bottom here we're left with square root of omega n square, which is basically zeta. Okay, the zeta here. So basically means sine theta equal to zeta, right? And which is the damping ratio, or theta equal to the inverse arc sine zeta. And we're talking about constant damping ratio, right? Constant damping ratio low C. So which means the zeta is being kept as a constant. Then guess what? If this is constant, that means the theta is constant, right? If theta is constant, basically means for any point along this line here, they all have the same what? Damping ratio. Okay? Yeah. So this is basically, it's the constant damping ratio locus in the S-plane. And then the question here is, how is this line here going to be mapped into the Z-plane, right? Okay. As a matter of fact, when I graduated from master program, I had an interview at a company called Creo, but now it's being combined with another company. I was interviewed by a question is, tell me the constant damping ratio low C. I completely flunked that question. So, because I didn't teach this stuff. Yeah. And apparently I didn't get a job, right? Yeah. But ended up doing a PhD. So. Ironic. Very ironic. Yeah. Okay, so now let's take a look. Think about the mapping out here, right? So coming back to the mapping, basically we're talking about this relationship again. Okay, z equal to e to the power ts, and I'm gonna substitute this s into this mapping out here. That's the result of a direct substitution. And now, okay, we're going to modify, manipulate this just very slightly without changing it, okay, just to manipulate it. Now remember, omega d is this quantity, omega n times square root 1 minus zeta squared. Okay. Now for the same expression in here, I can manipulate it to be this. No change at all. Okay, so if you substitute omega d over here, and you know omega s is related to the sampling time, which is 2 pi divided by sampling time t, you get exactly the same thing as this. Okay, yeah, you get exactly the same thing. The reason we wanted to do this is basically this is e to the power this whole chunk right here. We're talking about the constant damping ratio, right? So the damping ratio zeta here specifically being extracted out. Okay, so it shows up explicitly at here. Now for this complex number, okay, for this complex number, it basically any complex number, you have a magnitude for the complex number, and that's e to the power of this portion in here. That's your magnitude, right? And then angle, okay, of this complex number is 2 pi omega d over omega s. So it's a complex number which has magnitude this much and angle this much. And the magnitude at here, if you don't like lowering, right? If you don't like the exponential, it's basically the relationship is ln z equal to negative 2 pi zeta over 1 minus this, then omega d over omega s. Okay, same thing. Okay. Now, if you look at the magnitude and the angle at here, okay, zeta is a constant, so basically this portion is a constant here, right? It's a constant. So what this tells us is magnitude is it's a function, right? It's a function of what parameter? The omega d over omega s. Okay, that's basically what the magnitude is. The angle, same thing. It's also a function of this ratio ws over wd over ws. So both the magnitude and the angle are a function of the same parameter, omega d over omega s, right? Mathematically, you can basically, if you remember in algebra, okay, you can always write basically a formula like in polar coordinates. Okay, so r equal to a to the power of e b theta. Okay, yeah, and And so the A and B at here, okay, the A and B here are what? So A is this one here, and B is B theta, right? Will be this one here, okay? Yeah. So if you plot this one, you'll get a spiral equation basically. Okay, you get a spiral. So starting from origin and starting to spiraling out of it. Okay, so you get a spiral equation. Okay, so this mapping, right? For this, based on this mapping here, based on the magnitude, the angle here, what we would expect is we would expect basically a spiral equations, and that spiral equation depends on the value of this omega d over s and omega d over s here. Okay, yeah. So that's essentially what happens at here. Okay, for you substitute basically, for example, you let zeta equal to 0. Okay, you let zeta equal to 0, and you get a magnitude, this guy, and a magnitude of this one here, right? Sorry, angle of this. Then you can plot what will be this spiral corresponding to zeta equal to 0. Okay, yeah, that's basically the idea here. So, for example, let's say if I do this and I get this guy equal to, because when zeta equal to 0, right? Actually, when zeta equal to 0, what is the magnitude of the z here? Magnitude z when zeta equal to 0 is always what? Up to 0 here, e to the power of the, right? It's always 1, isn't it, right? Yeah. And if you look at this angle here, and that's hard to say, right? That's hard to say. That's completely depends on this omega d over omega s, right? Omega d over omega s. Okay. But either way, if I'm going to draw it, right? So for this particular one right here. So it really depends on this, of course, the angle, but it doesn't matter. So this is always a 1 here, right? So basically, you end up with just a circle, basically. Okay, yeah, spiral. The circle is a special case of circle, essentially, right? Okay, so for this particular one, if you have a different zeta value, okay, so this is basically corresponding to zeta equal to 0. Let's draw that a little bit again. A little better drawing here. Alright. And this is zeta equal to 0 right here. Okay. Now, if you have a different zeta, let's say zeta equal to 0.3. Okay. If you have zeta equal to 0.3 right here. Okay. If your zeta equal to 0.3. You actually, if you plot it out, okay, you're gonna get a spiral like this. Okay, I didn't finish, so you can keep basically circling here, and then at the end it will go back to 0. Okay, so that will be basically zeta equal to 0.3 at here. Okay, yeah. So that's the spiral this. Let's take a look at the very specific value. Okay, for let's say, for example, for if I have omega d over omega s equal to 0.25. Okay, so if I have omega d over omega s over equal to 25 here, then I can calculate. I can substitute basically zeta, and I can substitute the zeta and omega d over omega s into the magnitude and angle equation at here, right? Calculate what the magnitude is, what the angle is. So let's look at the angle. Angle is very easy. If I substitute 0.25 over here, so 2 pi times 0.25, and that gives us what? 0.5 pi, right? 0.5. So angle is 0.5, so which is pi over 2. Okay. And then magnitude, you can calculate, use your calculator, and then you get approximately 0.61. Okay, 0.61. So if I go back to this drawing at here, where is angle pi over 2? It's here, right? And where is the 0.61? It's over here. Okay, Yeah. So that basically is a special value, and this one here corresponds to omega d over omega s equal to 0.25. Okay, 0.25. And you can imagine for this particular point, what is the omega d over s, omega s ratio? 0.5, right? Because of pi. Okay. And you can calculate, you can do another calculation. What is this much of magnitude when the ratio is 0.5 and the zeta equal to 0.3, right? So that's how you basically construct this line at here, right? How you construct these lines. Okay. The other thing is, when we make actual usage, right? We don't really need to draw the bottom here, okay? So we only need to use the top half of the spiral here. So if you look at the whole spiral, it's going to look like this. But I only need the top portion. Why? If you look at this, this is basically from 0 to what? To pi here, right? So theta value goes from 0 to pi. And pi is the maximum frequency. So we don't need to worry too much beyond the maximum frequency anymore, right? So we only need to take the top portion of the spiral, okay, for different zeta value right here. And that's what you see. And this one here is what we're really interested in terms of the mapping at here, right? So constant damping loci is mapped to all of these clusters of the curves at here, which is a part of the spiral. Yes?
Beta was negative?
Negative? Yeah.
Do you care about the bottom?
Yeah. So basically, the bottom, what you do is just essentially just a mirror of that, right? Yeah. But theta negative or positive, it's actually just a mirror of each other, right? Yeah. It's good. Okay. So I need my mouse here. So just to jump ahead a little bit here, right? So this is the whole picture what we look like. See, this basically is the mirror of the top and the bottom here, right? Yeah. Don't worry, we'll come back to all of this middle, but this line at here, that's the constant damping ratio here, right? Okay. Yeah. Okay. That's type number 4, right? Let's look at type number 5, okay, which is the last type. And this is called constant natural frequency loci. Okay, constant natural frequency loci. Again, this has something to do with the second order system here. If I have a pose for second order system, omega n square root 1 minus zeta square. Good. Okay. So what does constant damping? What does constant natural frequency? Basically means the omega n at here is a constant, right? So this is omega n here is constant. Okay, that's constant natural frequency means. Okay. So how is that going to play into the mapping here? So let's look at basically this equation and this pose here, right? Now the real part, imaginary part. So if I do this, okay, if I calculate the magnitude here, so sigma square plus omega d square and then square root. And guess what do I end up with? So this square plus this square end up with omega n, right? Omega n here. So that basically means this is a constant, or the magnitude of this pole location, right, is a constant. So if I illustrate in the S-plane, okay, in the S-plane here, when, let's say, here is sigma, here is omega d, okay, here's sigma, here's omega d, okay. There is one situation that the magnitude, right, of this vector, of this portion, the length, it's a constant, which is omega n at here, okay, which is omega n. So it's a circle, basically. So if I finish this, I will get a circle. But I will only look at, let's say I'm going to only look at the left side of it here, okay? But overall, you know, you have a big circle right here, right? You got a big circle. But of course, we are only interested in the left side of the circle. That make sense? Yeah. Okay. So constant damping, constant natural frequency, basically constant natural frequency velocity basically means a circle here, right? A circle. So how is that circle going to be mapped into the z-plane then, right? As a matter of fact, I'm not gonna do the mathematical calculation at here. I'm gonna use that property, the conformal mapping. Okay, the conformal mapping. So here's a circle, right? Here's a circle, and the circle passing through that pole at here. And then what I just draw it here is I draw a line, what, passing through that pole, right? Passing through the pole. Guess what does this line means? That's right, constant damping ratio, right? And what is the relationship between this black and the blue one here? Perpendicular. And how is this black one being mapped into the z-plane? That make sense? So guess what? If this is z, let's say equal to 0.6, for example, right? And then for this particular circle in this plane at here, you should expect it's going to be a curve in the z-plane, and that curve will be in what relationship with this z equal to 2.6? Conformal mapping. So this one here is perpendicular to this, right? Then after the mapping, the mapped one should also be perpendicular to which one? To this one here. Okay? Yeah. As a matter of fact, this is 0.6. If I draw anything in here, if I draw any one of this, and each one of the lines here corresponding to a zeta, isn't it, right? Corresponding to zeta. And all of the zeta here will all be perpendicular to this circle here. So for the same circle here, if I'm going to map into the z-plane, it should be perpendicular to all of this at here, right? So all of this here, okay? Yeah. So that's essentially what the constant frequency velocity will be looking like after the mapping. So the bottom one here is zeta equal to 1. Okay, the bottom one here is zeta equal to 1, and then you can imagine. Let's see. Let's take a look at this special case here. Okay, let's think about the special case. So let's say this is a C point, this is A point. Okay, this is C point, this is A point here. Okay. First of all, where the C point will be mapped to in the z-plane. Okay, so C point means what? Means what value is equal to 0? So for C point, so for the C point at here, you are at the real axis, right? You're on the real axis at here, and the imaginary part is equal to 0. So the C point basically is a pole location S just equal to certain sigma 1, for example, right? Sigma 1 here. Then after the mapping, it's at where now? It's at e to the power sigma 1t, right? E to the power sigma 1t. And the angle is 0 degree, right? Angle is 0 degree at here. Okay? Am I right? Yeah, that's right. So if I after the mapping at here, so whatever sigma 1 is, and sigma 1 here is on the left side, and it's got to be within a unit circle. If this is 1 at here, so e to the power sigma 1 probably will be over here, right? Let's see. So this is where the C will be mapped to. Angle 0, right? Because C here has no imaginary part. So it's big. So plus, no, it's just 0. No 180. Yeah, just 0, because this is plus J0 here, right? So the C here has imaginary part to 0. And then after mapping, you get a 0 here, basically. Okay? Yeah. So C will be mapped to here. Okay? Yeah. And where would the A be mapped to? Okay? Where would the A be mapped? A is, real part is 0. So A at here has certain omega value, right? Has a certain omega value here. So let's call it, because we're talking about constant natural frequency, so apparently this is the magnitude, right? This is basically the radius. As a matter of fact, we can call sigma 1 to be the same as omega n, right? Yeah. So at this location, A location at here, the A at here, so S equal to just j omega n. So that's going to be mapped to e to the power of j omega n t. Okay? So that's going to be mapped to e to the power of j omega n t. Which means where the A location is going to be now. So A location will be, real part is 0, so the radius is 1, right? So A will be somewhere over here, but A will be where? On which circle? On the unit circle, right? Yeah, so the drawing here. So A will be here, and then with a angle at here, omega nt. Okay, omega nt. So that's two extreme, right? So from C and A locations, okay, will be mapped to here and here. Okay, here to here. And the rest of the location, right, between C and A, this part of the curve will be, as I said, so let's see if C is over here and A is over here, right? Then the rest of the curve between C and A will always be what? Perpendicular to each one of these constant damping ratio low C. So you would look like this a little bit, look like something like this. So it's perpendicular at each point. It's perpendicular to each one of the curve right here. Okay. If you have a different omega n, right? Different omega n, it may be starting here, or actually it's always on this side here. Okay, it will be here or here. It doesn't really matter. So that's where you see this drawing at here. So do you see this drawing now? This is basically this is essentially all of the different cases putting together here, right? When you started here and the angle, so you have this much, this strength you see here. That's basically how you maintaining the constant, maintaining this conformal mapping, the perpendicular relationship, right? Maintaining perpendicular relationship. So these are constant damping ratio low C, and this is basically the constant natural frequency low C. Okay, that's how the constant natural frequency low C being mapped to. Okay, yeah. Again, there's one more geometric relationship I can just make use of time in here, right? So let's say if this is C, okay? If this is a C location, if this is a C at here, and this is the A location, for example, okay? Yeah, this is A location. So A location corresponding to theta equal to how much again? Omega nt, right? The A location, as we just calculated. For the A location, it's omega nt. Okay, it's omega nt. Now, omega nt basically means if I connect origin to A location, how much angle between this? It's theta equal to omega nt. Okay. So now compare some of the relationship here. Okay. This curve is perpendicular to what? To this curve here, right? To this curve. And this OA at here, that's basically a reading line, right? The reading line here, it must be perpendicular to this curve too, isn't it, right? Then subsequently, this OA and this CA at the A location, they must be what? Parallel, but they touch each other.
Well,
tangent, right? Tangent. Yeah. So this OA must be tangent to this one here, right? To the natural frequency here. So you can try, basically if I connect this point to this point, they must be tangent too. Right? So it's the same thing. That make sense? Yeah. So this is how you can interpret this curve. Now in MATLAB, you can use a command called the zgrid to generate a graph look like this one here. Okay, look like this. So without anything else, just type in zgrid, you will generate a plot like this. How you can interpret the plot is okay. So if you look at the plot at here, right, and I want you to be able to interpret it, pay attention to the label on those at the edge of the outer circle here. So there's 0.1 pi over t, 0.2 pi over t, and up to pi over t. Okay? That's the label. And of course, you have a whole bunch of a constant damping ratio and a constant natural frequency, right? Okay. So what does this label here mean? You see, the A here I derive as what? Theta equal to omega n over t, right? So basically at this particular location or at any location, if you're given a theta, that omega n must be equal to theta over capital T, right? That's natural frequency. So that's how the label here come into the picture. Theta maximum is pi. So if you pick any point, this is essentially even it. So I'm trying to segment it into different values here. If you pick any point at here, and that corresponding omega n is theta over 2t. So at this location is 0.1 pi. So basically your omega n equal to 0.1 pi over capital T. So theta here is 0.1 pi. Okay, and that's the how the MATLAB graph here you can interpret it. How you can, what does this mean? What does this mean? Right? Numbers here. Is that good? Yeah. And that's the 5 different types, okay, that we wanted to cover it here. And I still have 5 minutes. Let's quickly go over the example. We can go over a little more in the next lecture, but okay, let's consider an example here.
so you essentially define all the corners in the
Yeah.
Usually X or Z plane.
Right. You actually, well, ideally you should try to plot it into this graph right here, and then you find the desired region for the poles that you're looking for. Yeah. Okay. So I'll show you one example here, right? Yeah. Okay. In this example, we have been given a continuous domain what we desire for. We want a zeta equal to 0.5 damping ratio. We also want a settling time, which is a 2% settling time, equal to how much second? 2 seconds. Okay. So minimum, basically, we want a minimum settling time 2 seconds at here. Sampling time, we're going to use 0.2 seconds. Okay. Okay. And let's find, okay, given these conditions that are here, let's find the desired pole locations, or the region of the pole locations in the Z plane. Okay, so just quickly, and I'll be able to finish the example here. But anyway, yeah, I'm using 2% settling time. So 2% settling time formula is this. So Ts equal to 4 over zeta omega n, and that is desired to be less than 2 seconds. Then from here, you get 4 over 2 times omega n. Okay. Sorry, what's going on here? No. So sorry, something here. So zeta is how much? 0.5, right? Zeta is 0.5 here. Okay, and that less than 2 seconds. Then I can derive my omega n constraint. In this case, will be more than what? 4 readings per second. Okay, so the natural frequency is desired to be more than 4 readings per second, and then you can derive your damped natural frequency. So substitute omega n, substitute zeta here, 3.464 okay, readings per second. Okay. Now let's consider the mapping now. So after the mapping, then what happens? Okay. After the mapping, you have basically this is a formula here. Okay, here's a formula. So I can calculate that absolute value of the mapping, so which is this portion right here. So e to the power negative 0.5 times 4 times 0. Sampling time is 0.2 and approximately 0.6703. Okay. And we can calculate the angle at here, which is omega dt, and that's 3.464 times 0.2, approximately 40 degree. And your poles at here, in this is the boundary here, so 0.5134 plus minus j, that plus, that's just plus here, 0.4308. Okay, 4308. That's some sort of hard calculation at here. Okay, the hard calculation. Okay, so now in terms of the mapping now, right? In terms of the mapping, you see, because we want our omega n to be more than 4 reading per second, okay, based on the given condition at here. And we want our damping ratio to be 0.5 at here, okay, to be 0.5, right? So if you're going to draw this, basically if you're going to draw this using this graph here, so first of all you draw out this 0.5 constant damping ratio at here. That's how you can draw this, right? And then you had also to find out the natural frequency locus corresponding to how much? To the 4 reading per second. Okay? Yeah. So that's what you see in my lecture notes. You should try to practice this portion in the MATLAB here. Plot this constant damping ratio. Plot natural frequency corresponding to 4 reading per second. And when we want the natural frequency more than that, right? So more than that basically means if you look at the train data here, what does more than mean? More than basically means this is a lower frequency, and when you go to the other side here, that's higher natural frequency. So basically, if I'm talking about the region at here, which region am I looking at? It's between this and this, which is this portion at here. Okay? Yeah. So that simple specification in the time domain will give you in the Z domain a region in the poles, which is here. Okay? That intersection between the constant damping ratio and the natural frequency is the calculation of the poles that we have it here. Okay? Yeah. So good? Okay, I have one more example to go, then we can talk about the next lecture.
So how are you doing the test for us?